shouldn't need this actually. So looks good. Like I said, we're still a little early, so we're just doing some checks and then wait a bit longer and see who joins us, and then we'll get going. So it'll just be a pause for 5 minutes or so. Thank you for sharing the link there, Kichong. Yeah. I hope people gave Anki a go and try to make some flashcards so that the stuff we cover will be remembered better. Thanks, Tyler. I think we also have a backup recording as a just in case, but I'm not 100% on that. I mean, I guess I can try and record somewhere. Don't know how though. Three backups, okay. I think that's plenty. Yeah, okay. Sounds good. Hope people had a nice weekend. Got some rest, ready for people's favorite day of the week, Monday. If there are leftover questions from last week, this would be a good time for people to ping those, if any, at the top of their minds. Just in this spare 5 minutes whilst we wait for other people to arrive, or any clarifications you want, or other things you just had questions about. To Noman's question, what we're hoping people to take away from this series, I think the most important stuff to take away is what we covered in the first session, and that's just kind of like the core idea of what SNARKs do, and that's the scalability and zero knowledge aspect. Like, how do they sort of work? Beyond that, it's a bit of a basic understanding into some of the inner workings, which is the mathematical concepts and stuff like that we're going to do in this session and the next session. And then lastly, is a bit more of a broader exploration of a few different proof systems that are out there in the last session. This is like a more beginner's introduction that's kind of like fairly broad and a very good basis, but it's trying to be in this intermediate spot of like more than a blog post, but not like a 6-week course, but a 6-hour course instead. Okay, so I mean, it's 3 past now, but I don't think it's entirely fair to always wait 5 minutes, 10 minutes for people to turn up for something that starts at a particular time. You know, generally speaking, we choose a particular time because that's when it's supposed to start. So I think we'll just kind of get going with this second session now that it's a few minutes past, and then stragglers will kind of come in afterwards. So welcome back for part 2. I hope you made some progress with understanding part 1 and all the content we went there, and also maybe making the flashcards like I recommended to help commit that stuff to memory so that it's with you when you need to discuss this topic, and so that otherwise you come to one of these courses, lessons, and then you learn it, you understand it, and you never practice the understanding again, and then it kind of goes. So then 3 weeks later, 3 months later, when you have a conversation about it, you can't properly engage with the discussion. Fran, I didn't fully understand the question. You're saying you wrote cards in Anki. Can you put the question here? If you've got a question about Anki, that's very welcome as well. Okay, interesting. What's the point of drawing a circuit if at the end of the day we must look for a solution of polynomials? The circuit represents the computation that we're going to claim we've completed, that we've done correctly. One of the ideas from the last lesson. The circuit that we draw encapsulates what we're saying we're going to do. Polynomials are used to transform this circuit into like a representation, and then we kind of conduct maths there to make this claim. We're not actually looking for a solution to the polynomials. Like if you filled it incorrectly, then you'll have a solution is kind of the key point. So they serve distinct roles. The circuit, the drawn out circuit, represents the computation that we're saying we completed, and the polynomials is how we're going to make the proof. That will hopefully become a bit clearer in the next couple lessons as we cover more of the mathematical foundations. Some general points. The course material is at this link. Keaton dropped this in the side chat, so if you don't have it, you can just check there. Again, feel free to stop me if you have any questions. If you put them in the chat, I will see them, so I will stop and speak about them there. So ask them as they arise. And if there's anything undermining your ability to understand me, whether that's audio or my drawing or anything like that, just let me know as well, and I can make more changes there. And then for asynchronous questions, there's the Intro to SNARKs channel in the PSC Discord. Is a good place to ask there. And if you @ me, I will get a notification and respond quickly. Before going into session 2, I just wanted to highlight a couple of the key points from lesson 1 and maybe a couple clarifications. I'll answer the Infinity's question after these clarifications. I didn't necessarily say all these things, but I want to emphasize them. So making proofs requires doing the computation that you said you were going to do, plus some additional work to make the proof. So it costs more than just doing the computation. And in fact, I say plus some additional work. It's not a small amount. It's a fairly large blow up. But the benefit of that additional work is that verifying the computation is now going to be very, very quick. So when does it make sense to do this? Well, there's 2 main places. If loads of people have to check the computation, then rather than have them all redo all the computation, if they all check a proof instead, and checking the proof is quicker than redoing the computation, we're going to gain value. Or if privacy is important and you don't want data to be revealed, then the computational blow-up factor is going to be worthwhile as well. And generally speaking, the larger a computation is, the more sense a zero-knowledge proof makes. Because for small things, like a transaction on Ethereum costs 21,000 gas, but verifying a PLONK proof takes 300,000 gas. So it's 15 times more expensive. So if you're just doing one transaction in a PLONK proof, then it's not going to be worthwhile. But the PLONK proof actually is a general computation. So the PLONK proof can have hundreds of transactions inside it. And if you do that, then it scales and you get a lot more value from it. So coming to these questions, can we do a manually construct a SNARK in the end? We can't do that necessarily as part of the course, but if you want to do it like separately yourselves outside, I'd be very happy to help answer questions. It will be like a really, really good learning exercise. You can try and implement like a basic version of PLONK. There is also a PLONK by hand series. At the end of the course material, there's a few links to a few different places. We try to put a few different links of types of things that people might be interested in. But we didn't want to be one of these things where there's like 30 links and you kind of don't know where to start. But that PLONK by hand is a very nice one to see because it's literally like written out how it would actually happen. Question, the verifier receives the commit. So if it receives the commit, it receives the witness within. So the verifier couldn't decrypt from the commitment. We're going to do that next session, understand the commitment a bit better. But in a sense, you get loads of data in the polynomial, and then we collapse it, commit it together into a single value, and that binds us to what the polynomial was. Because if we make changes to the original polynomial now, the commitment's not going to work as it's supposed to work. But you can't just take the commitment and go back to the values. Okay. But we're going to cover the polynomial or the commitments in more detail on Thursday. And then we can get going with session 2 now. The core point of session 2 and also session 3 this Thursday is going to be to go dive into some of the mathematics that we're going to be working with. And it's not straightforward. We're going to be covering a lot of stuff. And like I mentioned last time, we keep building on stuff, and we really do that a lot here. We're going to start with modular arithmetic, and then that's going to be used in something called a group, and a group's going to be sort of used in something called a field, and the field's sort of used in the polynomials, and there's a theorem about polynomials. So we're really going to be building a pyramid, and this is why you really need to like understand the fundamentals as well as possible so that we can grow this pyramid more effectively. And we're covering the mathematical objects and tools that we need more specifically for PLONK. So different proof systems that are out there will use different mathematical ideas or systems. There's a lot of overlap between different types or certain types of systems. And the ones used in PLONK are seen in a variety of other places as well. So they're going to be quite useful. And again, for PLONK, I may have mentioned this on last week, but the reason why we chose PLONK is because it's a much more intuitive system compared to the other ones. Specifically in the arithmetization from last lesson, when we make the circuit from the addition multiplication gates, that's kind of like nice to think about. Previous systems like Graph 16, they use something called rank 1 constraint system arithmetization, and it's like a larger matrix, and it's like a sum you multiply two sums together, and it's just yeah, much less intuitive. But so that's why we're choosing PLONK, because it just kind of fits nicer to work with in terms of passing understanding, particularly a visual understanding. So we're going to go with modular arithmetic as the first kind of object we want to understand. And this is also known as clock maths, right? Because we're going to be going around in a clock. If you're, I mean, I think you're basically all developers, in which case you probably understand this decently, because if you've worked with like an i8 or a U32 or whichever, you know that once you hit with an i8, you know, you have, or U8, let's say, you've got 8 bits. And once you pass the 8th bit, you can't just make the number bigger. You actually just wrap around and go back to 0. The same thing's gonna happen here. But we want to understand this in a bit better detail. I couldn't copy the GIFs across to the presentation, but we're going to be sketching this all out by hand. And I do recommend in the course content online, if you can look at the GIFs, it does help a lot, like this one here. So in modular arithmetic, we have a set of non-negative whole numbers like 0, 1, 2, 3, and 4. And I say non-negative rather than positive because we include 0. 0 is like technically not positive or negative. So non-negative means like all positive numbers and 0. And we want this to be whole numbers. During the introduction of the maths, there's a variety of simplifications I make that basically say it ignores the truth, which is, way more complex, and I would have to explain all these different things. So sometimes I'll just say, I'll give definitions that are more specific to what we want to work with, so you don't get overwhelmed with all these different changes, because a lot of maths is like very abstract, and that's so that it can be used everywhere, but we're only interested in the setting of SNARKs. So if we have this set, the 0, 1, 2, 3, 4, because we have 5 numbers in it, when we get to 5, when counting upwards, we just go back to 0. Okay, and this GIF in the online content, you can kind of see it wrap around. This is also why the set of 5 numbers doesn't have the number 5. We treat number 5 as the same as 0, as we do in programming as well, where the 0th position is actually the first position. So we can try and do a bit of a sketch here. Probably just zoom in a bit. To be modular arithmetic. And I said we can work with 0, 1, 2, 3, 4. And when we count, we have 0, 1, 2, 3, 4. We don't have 5. We just kind of go back to 0. Right? In a sense, what we're doing is we have the number line of 0 to 5. Well, I mean, the number line actually goes everywhere. But we extract this portion, so we're left with 0 to 5. And then we just kind of bend it into, that's a bad circle, a circle, 0. So that these two ends are connected together. Usually we actually have 0 at the top, but I've drawn it at the bottom here. Okay, and that's why when we count, we go 1, 2, 3, 4, 5. Oh, sorry, that's too many steps there. We start at 0. We get a 1, 2, 3, 4, and then we end up back at 5. Okay, so actually the visual online in the course material is actually more helpful. A very effective way to think about this is in this modular arithmetic set, we have one important rule. Because this has 5 numbers, we say that 5 is the same as 0 mod 5. Okay, and this equal sign is different on purpose. It has 3 lines here and not 2, because it doesn't mean equal exactly. It means something quite similar, which we say it means it's equivalent to 0 under this setting. And to specify the modular arithmetic space that we're working in, we have this mod 5, which means modulo 5. Okay, so the other example in the online GIF is we've got this set up to 10 that doesn't include 11, and you can try and guess what the rule here should be. It's going to be that 11 is congruent to 0 mod 5. So if you're going to be working with SNARKs, being able to do arithmetic in this space is important to find it very easy. In the same way you add normal numbers when you're working in just normal settings, if you're working with SNARKs, you want to be able to understand this idea very, very easily, such that you can just kind of straightforward just figure out how you're going to have to account for things. Okay, but this rule encapsulates most of what's happening in modular arithmetic. So the reason why we can just use this rule instead is that if we're in this setting where 11 is congruent to 0 mod 5, if we do like 4 times 5, well, that equals 20. But then how do we get back into our set? Well, 20 equals 11 plus 9. Oh, sorry, I put mod 5 here. That's oops. That should have been a mod 11. +11 9. But because of this rule again, 11 is congruent to 0 plus 9, right? And that just equals 9 mod 11. Okay. If we work in the smaller group, the mod 5, we can do like 2 times by 3 equals 6. Well, 6 is bigger than 5, so we've got an issue. But we know that 5 plus 1 is the same as 6. And that's congruent to 0 plus 1, the same as 1 mod 5. And you can, keep doing this as it gets larger. If you have 3 times 4, which is 12, well, we can see this is 5 plus 5 plus 2, right, which is equivalent to 0 plus 0 plus 2, which is the same as 2 mod 5. Okay, just how many 5s go into it? And I wrote 5 plus 5, but we could also just do 2 times by 5 plus 2, which we know will be 0 plus 2. And that equals 2 mod 5. Okay, so you want to get used to working in these groups. Sorry, in this setting of modular arithmetic. We're going to do groups next. Okay, so this is like the base case. So we're no longer doing arithmetic on the normal numbers, the real numbers from minus infinity to positive infinity with all the decimal numbers in between and things like that. We are working now in just like a small set. Well, for right now, in the examples, the small set 0, 1, 2, 3, 4, or up to 10, with this rule. Okay, and then we're going to keep building from here to add more structure so that we can work with these objects in more interesting ways. So from modular arithmetic, we go to groups. And the groups kind of take modular arithmetic and add more structure to it. And that structure is going to be very useful to us. The modular arithmetic just defines how we handle addition and multiplication. But the group has more things, and it's got 3 things inside it. We've got the set, which in the previous example, one of them was 0, 1, 2, 3, 4. That's the set of numbers that we're working with. We've got a binary operation, for example, addition and multiplication. The binary, all it means is that you take in 2 things and you get out 1 thing. So, because binary is 2. Addition is binary because you take in 2 numbers and you add them together and you get out 1 number. Same as multiplication. And that in the parentheses at the end, I say, but not both. In a group, you only have 1 of these operations. You don't have addition and multiplication. You'll just choose 1 of them. So mathematical groups are way more abstract because there are tons and tons of binary operations we can choose from. But like I said, in our setting, all we care about is addition or multiplication. So the fact that others exist doesn't matter to us. And then lastly, we need something called an identity element. And this sounds a bit confusing, although when you see an example, hopefully it'll be way more straightforward. But the identity element, when it's used in the binary operation, be it addition or multiplication, it should do nothing. Okay, so in addition, we're going to have to add, if we add the identity element, we should get out the same number we started with. So if we're going to do 3 plus something, plus the identity element, we should get out 3. Okay, so hopefully that will be clear to you once you think about it a bit. Is that it's going to be 0. Okay, but we're going to do a live sketch to make this a bit clearer. Okay, so there's going to be a lot of live sketching this lesson and next lesson as we go through these mathematical objects. Groups. And I said, so we're going to take this set is just going to be 0, 1, 2. So it's a very, very small set we're going to work with here. And it's going to be modular arithmetic. So the rule here is going to be 3 is congruent to 0. Sorry, it's equivalent to 0 mod 3. Let's take addition as our binary operation. And I said we need an identity element. I said that was going to be 0. Okay, so we can check that 0 is indeed the identity element, because if we do 1 plus 0, we get out 1, which is exactly what was supposed to happen. And if we do 2 plus 0, we get out 2. The output is the same as the input. And the same here. So, so 0 is indeed our identity element. It'll be good to ask yourself quickly, what if instead of addition, we use multiplication? Then what would the identity element be? Well, it would be the number such that 1 multiplied by x equals 1. So the question here is, what is x? And hopefully you can see that x is going to be 1 here. Yeah, well done, Ela. So, I mean, that's fairly straightforward. But this should hold for whatever the input is. So we can check that if 2 times 1, is this going to be 2? Yeah, we get out 2. So if x is 1, the identity element, okay, it should always be the case. But you might realize now that actually if we check and we do 0 multiplied by 1, we get out 0. We don't get out 1. Sorry, we don't get out. Hang on, what am I trying to explain here? Okay, no, scratch that. Sorry, ignore that. We get the same thing that we wanted here. So this is okay. In all 3 scenarios, there's only 3 possible multiplications we can do here with 1. 0 times by 1, 1 times by 1, and 2 times by 1. And in all 3 of them, we get back the number we started with. So we have an identity element here as well. Okay, we're not actually done with groups yet. That's not actually what a group is. And we're going to come to these next rules. These are just the things contained within a group. We have the set. We've got the set. We've got the binary operation, and we've got the identity element. Okay. In our example, is 3 identity element. Remember that the identity element is tied to the binary operation. So are you talking about under addition or under multiplication? So just get the answer there. So under addition, let's just do this in whatever this color is. The left side is our addition. So let's look what you're asking. You're asking if 3 is an identity element. 3, well, hang on. We already said that 0 is the identity element. But we also, because we're in the modular arithmetic group, 3 is congruent to 0 mod 3. So under our setting in modular addition, 3 and 0 are actually the same thing. So 3 is also the identity element, but we'll never actually work with 3 because we try and stick with the numbers in our set. And if 3 is the same thing as 0, then we'll just use 0 instead. So when we're working with these sets, just try and stick and only use numbers that are inside them. Okay, similar to like an I8 or U8, you know, if you're a programmer. because things wrap around, larger numbers are the same thing as the smaller numbers that have the same mod under the 2 to the 8. Okay, so, but we're not actually done with groups yet. That's just the objects it contains. We're going to add a couple of rules. Firstly, there's the notion of an inverse element. So again, inverse is you're undoing something, but what are you undoing? This is again going to be tied to the binary operation. So it's going to be tied to addition and tied to multiplication. And you maybe have already sort of guessed that undoing addition, well, that sort of sounds like subtraction. And undoing multiplication sort of sounds like division. And that is going to be the case. And it's this additional structure is why we only need addition and multiplication and not subtraction or division, because we're going to have the same thing as subtraction and the same thing as division using these inverse elements. So let's look at an example of what those might be. Let's go back to blue. So in our addition example, if we're looking for an inverse element of 1, this is going to be 1 plus x. There's another step here, because if you're undoing, then like, what do you get back to? Well, we have to get back to the identity element. Okay, so under addition, 0 is the identity element, because anything adds 0 is the same thing as what you started with. So anything that satisfies this equation is going to be x is the inverse element of 1. And then I should actually go on here and say under addition, or call it the additive inverse element, in the modular set 0, 1, 2. Okay. And what's it going to be here? Well, we've got to find something to add to 1 to get out 0. But remember that 0 is also equal to 3 under our setting. So since 1 plus 2 equals 3, which is congruent to 0 mod 3, then 2 is the inverse element. Well, the additive, let's say. And so again, see here that we actually just did subtraction. Because 1 minus 1 is 0, but also here in the same place, 1 plus 2 is 0. So we don't need the notion of subtraction, because we're going to have something called the additive inverse. Now, this is actually a bit of a small group with 3 numbers, but perhaps working in a bit of a larger group would add a bit more clarity. We can do it in a larger group after this. But let's just continue from this example. What's the inverse of 2? 2 plus x equals 0. We're going to find something that satisfies this. Maybe some of you can kind of figure it out, but we're going to do the same thing, because we know that 3 is the same thing as 0. 2 plus 1 is 3, which is congruent to 0 mod 3. Right? And these are actually... Yeah, it's 1. These are actually, if it goes both ways. If 2 is the inverse of 1, then 1 is going to be the inverse of 2. So they're actually sort of connected to each other by nature. And 0, we can also check 0 as well. 0 plus x is 0. But because 0 it's 0, it's the identity element anyway. The inverse of 0 is itself. So minus 0 is the same thing. Let's just write that up. Minus 0 is the same as plus 0. Plus 2 is the same as minus 1, and plus 1 is the same as minus 2. Okay. Because we're mod 3, we just have to like add a number to get to 3. It's sort of fairly straightforward. And if we're going to be working in the modular group with 5 elements, you want to find the additive inverse of 1. You just got to do 1 plus what equals 5, which is going to be 4. So with addition, it's more straightforward. With multiplication, it gets a little bit harder. Let's see. What we're going to want to find 1 times something equals, what are we supposed to get out? Well, we're under multiplication and we're supposed to get back the identity element, which is the multiplicative identity element, which in this case is 1. So 1 times what equals 1? Well, I mean, obviously 1 times 1 equals 1. So I can expand on that now, but it'll probably be a bit clearer to do 2 first. 2 times x equals 1. What's going to be, what possible values for x could we get here? We can try, and we can just try multiples of 2 until we get there. I mean, 2 is not, sorry, we get to 4. Oh, but hang on, but 4 is the same thing as 3 plus 1. Okay, but in this scenario, that's congruent to 0 plus 1, right, which is the same thing as 1 mod 3. Okay. So I know there's not immediately straightforward. And in this, these are the places where math is very much like programming. You really have to try and like grab ideas yourself or examples and play around with them yourself to grasp them more effectively. We're going to do another example afterwards using a bit of the group with 5 elements, sorry, the set with 5 elements. So it will be hopefully a bit clearer with that one as well. And to Jimmy's question now, are we saying that x is x a fraction? X needs to be in the set, right? And this is our set 0, 1, 2. We don't contain any fractions there. Again, like I said, we're going to do division without needing division. So instead of dividing by 2, we can multiply by something and it'll be the same as dividing by 2. Normally, you'd multiply by a half, which is a fraction. But in our sets, they have particular structure that means we don't need to multiply by a half. There'll be another whole number that we can multiply by and it'll be the same as dividing by 2. So this here, we think that x should be a half, a fraction. But it turns out that 2 is multiplying by 2 is the same as divide by 2 in our set, in our modular arithmetic setting. Okay, so the more and more examples you see of this, hopefully the more and more comfortable you get with it. But we're not fully done yet. I said that the rule is actually, okay, sorry, we're just introducing the idea of an inverse, which is related to the binary operation. Okay, so that's what an inverse is, and then we're going to like finalize what actually a group is. If something's actually going to be a group, it needs to have 2 rules that it satisfies. Every element every element has to have an inverse element according to the binary operation. Okay, and every element that you get out of the binary operation should also be in the set. Okay, so now let's see if we actually have sets. Let's take a different example. Here we're going to do 0, 1, 2, 3, 4. Okay, and we're going to do this with addition, and we know that 0 is going to be the identity element. Okay, so is this a group? Is the question we're now asking ourselves. we've got to see whether it satisfies the two rules we just set out. One, does every element have an inverse? Two, is every output from the binary operation in the set? Okay, that's what we want to check. And we can just do this brute force because there's not that many things to consider here. So one, does every element have an inverse? Well, the inverse is tied to the binary operation, which is addition in this case. So 1 plus x equals 0. Because remember, that's the equation we've got to satisfy to find an inverse. Well, we know that 1 plus 4 is 5, which in our setting is congruent to 0 mod 5. Because remember, in this modular setting, we have the same thing. Our primary rule is that 5 is congruent to, equivalent to 0 mod 5. Okay. If you can, before I say them, try and work out the other additive inverses here. So what about 2? 2 plus x is 0. Well, we know that 2 plus 3 is 5, which is congruent to 0 mod 4, mod 5. Okay, and what about the case for 3? 3 plus what is 0? Well, I said that these also, they work with each other. So if 3 is the inverse of 2, then 2 is going to be the inverse of 3. So 3 plus 2 is 5, congruent to 0 mod 5. Same thing for 4, because 4 is the inverse of 1. 4 plus 1 is 5, congruent to 0 mod 5. So our first rule, I mean, also 0 plus 0 equals 0. So 0 does have an inverse element. Our first rule is satisfied. And then the second rule is everything from the output from the binary operation in the set. We've got to check if 0 plus 1, 0 plus 2, 0 plus 3, 0 plus 4, and 1 plus 2, 1 plus 3, plus 1 plus 4, etc. The result of all of those are in the set. But we have that because of the modular arithmetic that we were doing anyway. You can write that out if you want, but that's sort of inherited from the modular aspect of things. So this object is a group. We've got a set there. We've got our operation, binary operation, and we've got the identity element of the operation. And everything in the set contains or has an inverse element. Okay, what about if we do multiplication and multiplicative? Identity is 1. Well, when we take a look, we're going to want to find inverses again. So 1 times by x equals 1. How are we going to solve this? Well, I mean, of course, 1 times by 1 equals 1. So I'm going to do this notation here to the power minus 1. That's the same as saying like dividing by 1 is the same as multiplying by 1. This is like the inverse, the division thing, because it's going to be the same thing as division. What about for 2? 2 times x equals 1. Well, what do we have here? Well, let's just reiterate to make sure we know. In our group, we have that, sorry, in our modular setting, we have that 5 is equivalent to 0 mod 5. So what are we going to do? Well, we can just go through multiples of 2 until we either find one or don't find one. So 2 is not 1. 4 is also not 1. 6. Well, actually 6 is the same thing as 5 plus 1, which is congruent to 0 plus 1, which is 1 mod 5. Okay, I mean, this here was just 2 times 1, and that's 2 times 2, and 2 times 3. Okay, I was just going through the multiples to try and find the inverse of 2, right? So we can also sort of say that 2, the inverse is 3, because 2 times 3 is 6, which is the same thing as 1. To Noman's question, does using modular arithmetic create or allow the existence of these sets and groups that have certain mathematical properties we then exploit to do one-way maths? I mean, modular arithmetic, it contains the set that you're working with. In many ways, modular arithmetic just takes all whole numbers, and then adds in this rule where 5 equals 0, or where 11 equals 0, or where 3 equals 0. And then normal arithmetic applies. So it doesn't really create the existence of something. It's more taking something that does exist and modifying it a little bit. Yeah, I'm not entirely sure exactly what the question is. So if that's not too helpful, you can try and rephrase it maybe. But we're not done in our example yet. We're trying to see if this set with multiplication and 1 is a group. So we found an inverse for 1. It turns out to be 1. We found an inverse for 2. It turns out to be 3. We now want to find an inverse for 3. But we said it goes both ways. So if 3 is the inverse of 2, then 2 is going to be the inverse of 3. So we can just check that. So if we do 3 times 2, well, that's 6. It's going to be congruent to, well, sorry, I should try and be consistent. That's the same thing as 5 plus 1, equivalent to 0 plus 1, which is 1 mod 5. Right, so the inverse of 3 is 2. And what about 4? 4 times x equals 1. Well, not immediately clear. So we can just go through the multiples of 4 until we either find one or don't. So we've got, let me just write it out in totality. 1 times 4 is 4, which is not 1. 2 times 4 is 8, which is 5 plus 3, which is congruent to 3, so that's not quite it. 3 times 4 is 12, which is 2 times 5 plus 2 is congruent to 2, so that's not it. And 4 times 4 is 16, which is 3 times 5 plus 1. And that is congruent to 0 plus 1, which is 1 mod 5. So the inverse of 4 is 4 itself, apparently. Okay, so 1, 2, 3, and 4 all have inverse elements. But what about 0? 0 times x equals 1. And then if we start to think about this a little bit, we'll hopefully realize that if you ever multiply by 0, the only thing you can get out is 0. Like when you take 0 lots of something, you're only ever going to have 0. So 0 doesn't have a multiplicative inverse element. So this is not a group. Right? Why? Because 0 doesn't have a multiplicative inverse. We can turn it into a group if we just remove 0 from our set. Because everything else had an inverse element, right? And that would actually be consistent. Then we would have a group. But 0, 1, 2, 3, 4 with multiplication and 1 is not a group. Okay? So that's groups. We've got a set, we've got a binary operation, we've got identity element, and then it's got to have these rules where every element has an inverse element. Okay, which you've got to kind of manually check, at least in the beginning. Right, but the inverse elements are how we do subtraction and division. Okay, so again, to get more comfortable with these ideas, you're going to have to start like going over a few examples yourself when you can. This isn't immediately obvious. Like it takes a while to get used to these ideas. Don't expect for it to be obvious immediately. It will take some time and effort. Oops. Okay, so we've done modular arithmetic and we've done groups. Okay, I mean, yeah, this was time permitting. We don't really have time to do this, so I'm going to skip this. It will be an additional exploration. Next up is a field. And a field is kind of like getting two groups and just smushing them together into one thing. So the group had three objects inside it. It had a set, it had a binary operation, and it had an identity element. The field has five things. It's got a set, and it's got two binary operations instead of one, and it's got two identity elements instead of one. And of course, the identity elements are tied to the binary operations. So for us, the binary operations are going to be addition and multiplication, and the identity elements are going to be 0 and 1. So again, we're building up more structures of these objects. In terms of rules, the similar rules apply. Everything that you get out of the binary operations has to also be in the set. And also, everything has to have an inverse. And now we don't have one type of inverse, we've got two types of inverse. Everything needs to have an additive inverse as well as a binary inverse, except for one exception, which is that 0 doesn't need to have a multiplicative inverse. And in terms of the live sketch for this, we've already done all the work here. Like in this left side, we know that with the set 0, 1, 2, 3, 4, they all have, you know, this modular arithmetic setting, they all have an additive inverse, and that all results from addition are still in the set. And on the right-hand side, we've also already done all the work. We know that everything has a multiplicative inverse. We found them all here, except for 0. But that was the one exception to the rule, that 0 doesn't need to have a multiplicative inverse. And the reason it doesn't need to have an inverse, multiplicative inverse, is because it can't, like by definition of how this stuff works. It's like a very unique thing. It would be great practice for yourselves if you have time to try and see if something else is a field or a group. You know, this is the modular arithmetic with 5 elements. Maybe try and do it with 6 elements and also with 7 elements. You should find that the one with 6 elements is not a field, but the one with 7 elements is. What you will find is that it's only ever a field if the number of elements is prime. This is why we use prime numbers everywhere. Well, one of the reasons that we use prime numbers everywhere. Because if the set itself is prime, you're always going to have these inverse elements. It's not fully true. It's not just primes. It's also prime powers. So, you know, 4 is not a prime number, but it equals 2 squared. So it will be a field. But 6 is no, I mean, you have a field with 4 elements in it, but 6 is 2 times 3, and that's 2 different primes, so it doesn't work. Okay. Funny question, zkSNARKs. If you want an example of elliptic curves are going to be an example of a group that is not based on modular arithmetic. The thing is, if you're using normal numbers, we're usually just doing additional multiplication, so it's hard to get away from that kind of stuff and it just being modular arithmetic. But we're going to do it with a group. But groups are like a very, very abstract idea. They're a big part of like fundamental theoretical physics, like the understanding of the universe. And essential particles, they have like this symmetry group. So you can see the like rotation of an object. Sorry, this is like a USB drive. You can see the rotation of an object as a group, because if I can rotate it 90 degrees and then another 90, which is 180, and then to 270, and then to 360. And I can also turn it this way around. So instead of like in modular arithmetic, we do like a number plus one, plus one, plus one, and we keep doing that to find other elements in the set. In this scenario, it's the position, like the orientation of the object, where we have this, and you can rotate it once and rotate it twice, and then three, and then four. So that's why a lot of these definitions are like extremely abstract, because we will actually just write a letter in maths. We'll just say that we have the element A, which is very much uncomfortable for people who are new to it, because we'd rather work with an actual number. But there's really, it can be very, very abstract. So we're at 54 minutes. I think it's best to take a short break now and have questions before we go into the second part, where we're going to do polynomials and the Schwartz-Zippel lemma. But these ideas just keep building up, so you really want to like make foundations. So let's say that we'll restart again at 9, and we've got these 6 minutes just for you guys to have a little break or to ask more questions and clarify. I mean, I can go over another example in this short window if people want that as well. As for how they're going to come and connect in the context of SNARKs is SNARKs don't work with like normal numbers. They'll work with elements from a group. And again, so the reason why we only have addition and multiplication gates is that because we're working in a field, we can do division and subtraction using the inverse elements instead. Okay, so those ideas are integral to how we use SNARKs. We're just working with abstract algebra, and all in SNARKs we don't use the number 3. We use the number 3 in a field, or in a particular field, or the third element in a group, an elliptic curve group. So we don't really use normal numbers in SNARKs. I mean, that's like a very high level, potentially not too useful. But because, like I said, these ideas just keep building up and up. In order to explain how we use them later, we first need to know sort of this idea and then some other ideas for this to make sense. Otherwise, I can say things, but it won't actually mean anything. Because we're gonna represent all our computation using field elements, and then we're gonna map them to a group And then we're going to represent all of this. So we'll represent it all as a polynomial, and then we're going to map it to a group. And then we're going to check this stuff based on rules and theorems that apply to fields. So this is the language we use in SNARKs. Fields and groups are used in every, but as far as I can think of right now, every SNARK there is. Polynomials are not used in all SNARKs, but you can, the ones that don't use polynomials, you can think about what's happening in terms of polynomials as well from certain senses. In such a set 0, 1, 2, 3, 4, when finding the inverse of 4, we found 4. And we wrote the answer as 3 times 4 plus 1. Are the multiples of 4 countable when we write the answer? Let me just check. So, just want to check. So, I think you're talking about this here, where we found the inverse of 4, right? So we found 4. We wrote the answer as 3 times 4. This 3 times 4 here, if that's what you're referring to, that's not our answer. We checked 3 times 4 and it gave us 12, which is the same as 2 times 5 plus 2, which is congruent to 2. So that wasn't our answer. It was the one below where we have 4 times 4, which gives us 16. Turns out to be 3 times 5 plus 1. 3 times 5. Oh, right. So okay. This 3 times 5 here, essentially what I was doing before with this equals, so 16 equals, what I was doing before is I was trying to lay out like every single detailed step where 16 is actually 5 plus 5 plus 5 plus 1, which according to our rule, because 5 is the same thing as 0, this is congruent to 0 plus 0 plus 0 plus 1. Right, and it will just keep kind of growing like that. But instead of doing 5 plus 5 plus 5, I just collapse it into 3 times 5. The point is that's going to be 0 anyway, so we're just trying to put all the zeros together and then ignore them. Well, not ignore them, but treat them as 0. Okay. It is now 9. I know that's not... Yeah, it's a quick 5-minute break. So yeah, the maths, it moves pretty fast. So when mathematicians learn fields and groups, they take it quite slowly. They do tons of examples. There's like a whole course for groups and a whole course for fields. But when physicists learn these things, they also do groups and fields in like the first lecture, and it's kind of like hand waved and done very, very quickly because they don't need to know all the details really. They just need to know a bit of basics about how they're defined and how to work with them. Of course, the deeper your understanding, the better, because if you're going to be working with these ideas at a higher level, you want to be as comfortable with them as possible. But you can build that. Like the basic overview and definition is a really good starting point. So I just close the screen share. Share your screen. One moment. And believe we're back now, yeah. So in this second half, we're going to be going over polynomials and then this theorem. We introduced polynomials last lecture, but we're not interested in all possible polynomials. We're going to have another condition, and surprise, surprise, we're going to be restricting ourselves to ones that work with fields. Okay, so let's just go and sketch this sketch. Oops. Sketch out what we're talking about. So polynomials. Well, like we said last lesson, let's do P of X. Is going to have an example is like 3 plus 4x plus 7x squared. Okay, we've got x as the variable. Right, we've got x and x squared because x is a variable here. We cannot actually have like multiple variable p of x comma y, which is, only 3 plus 2xy plus 4x squared. But we're not really interested in those a lot of the time. We can just restrict ourselves to single variables, so just x. And these powers, there's actually a 1 here. These powers are whole numbers. Okay, so that's what we said a polynomial was. We're actually interested in a subset of all polynomials, like I just said, and the restriction is that the coefficients, the numbers in front of the variables, so 4 and 7, and you don't see an x here, but this is actually x to the 0. Anything to the power 0 is 1, so we can treat that as the x to the 0 term. So 3 is also sort of a coefficient. All of these have to be in a field. Okay, they've got to be in a field. For notation, we just figured out that this is a group over here. This this with also addition and 0, we call that field, we do this f with these 2 lines, and then underscore, and we put a 5 because it's the field with 5 elements in it. So this means 0, 1, 2, 3, 4, with additional multiplication, and 0 and 1 as the identity elements. Okay, so for example, here we might be interested in f, in these being in a field. For example, F11. Okay, so 3, 4, and 7 are all clearly in F11. And then the notation here is that we want P of X to be in F11 square brackets with an X inside it. This is the notation for the polynomials that we're interested in. Again, it might look a little scary, but it's just saying that it's a polynomial where all the polynomial in X, just one variable, where all the coefficients are in F11. So this one here, this polynomial is in the desired set of polynomials. Let's take some other ones. F of x equals 20 plus 14x cubed. Is this in our set, or in our desired polynomial area? Hopefully by now you're getting a little bit more comfortable. Well, in F11, we have that 11 is congruent to 0 mod 11. So this actually equals, well, is equivalent to 9 plus 5 x cubed. Okay, so this is an acceptable polynomial. What about g of x equals 3 plus x to the 1.4? Well, no, we can't have powers that are not whole numbers. What about h of x, which is 2 plus x to the minus 1? Minus 1 is a whole number, but it's negative. That's not actually allowed. And if you have a negative, it's actually the same thing as doing 2 plus 1 over x. It's the same as like dividing. Like we have the notation of the multiplicative inverse before as division. That's not a polynomial. The powers of x have to be, again, non-negative whole numbers. Okay. And then maybe if j of x equals 3, a very bad 3, is this a polynomial? And you might be wondering, because it doesn't contain an x term, that it's not, but it is still a polynomial. It's a very simple one. It's a constant one. It's a very, very easy one. Also, polynomial is a really kind of scary word. Like, it just sounds a bit bad, but it just means function. Like, you probably worked with lots of functions in school that was f of x equals this thing. That's, it's a subset of functions. Polynomials are a subset of all functions. Right, and sorry, to Clinton's question, we can just keep adding terms here, 4x cubed plus plus 2x to the 100. We can just keep going up and up. And even if we're working in an F11, we can have higher power terms of x, because that's still going to be useful to us. These are still going to be different things. Okay, so even though the numbers the coefficients will be between 0 and 10 in our example, we're working in F11, the field with 11 elements, the powers of x can just go up to infinity. But of course, when you have a concrete polynomial, like a specific instance of a polynomial, there is a largest power, and this has a name, and we say that the degree of let's do this, f of x is 3, because the highest power of x in this polynomial is 3. In a bit shorter hand notation, we do deg of of f equals 3. Okay, so the highest power, and so the degree of p up here would be 100, because that's the highest power. Okay, so the degree is also an important term. Sorry, when I said concrete polynomial, I meant like when I'm writing p of x here, it's kind of abstract. I'm saying it could do this and just saying, it could go up to anything. But a concrete polynomial is like, if you actually hand me a polynomial, it's already decided what the polynomial is defined as. Okay, a specific instance of a polynomial, rather than just like talking about some abstract potential polynomial. So concrete's not like a maths term. That's me trying to explain that I mean like one that's already been defined. Right, so this is the polynomial ring, which means that, it's polynomial in x, and f11 is where the coefficient can come from. And degree is another term that we want to remember. Oh, I didn't do a minus value here. We show that 20 and 14 are the same as 9 and 5. If we had minus 3, okay, let's just do a quick example. If we had f of x equals 4 minus 2x squared, then is this a polynomial? Well, it is, because again, modular arithmetic, because we're going to have, this is the same as 4 plus 9x squared. Okay, so this is like the additive inverse of 9. Of 2, sorry, is 9. That it would be good to try and understand yourself at home, just to get a bit more comfortable with these ideas again. And we can also evaluate polynomials, obviously. So if we take, let's stick with this f of x. What was it? 20 plus 14. Let's do 20 plus 14x rather than x squared. We can evaluate in our polynomial. Sorry, we don't want to use 20, do we? We want to use 11 and 5. 11 plus 5. Sorry, 9 plus 5. Not bad. 9 plus 5x. Okay, we can evaluate in our polynomial. We can do f of 3, which equals 9 plus 5 times 3, which is 9 plus 15, which is 24, which is the same thing as 2 multiplied by 11 plus 2, and that's going to be congruent to 2 mod 11. Okay. I put in 3, which is sort of like just any number. We can do this at f of 1.2, and then we get 9 plus 5 times 1.2, which 9 plus 6, which is 15. But we really shouldn't be putting in 1.2, and we also shouldn't be putting in like 3 as some whole number. Probably won't be a surprise, but we're only really interested in evaluating our polynomials at values in some field. And probably we're just going to use the field that the polynomial is associated with. So if our polynomial f of x, if f of x is in f11 of x, we're probably just going to evaluate at values in f11. Okay. So we can evaluate our polynomials. And to get more abstract, we don't even have to actually evaluate polynomials at numbers. We can actually do evaluation of a polynomial at the abstract example group that I mentioned before, which is rotations of an object. You know, because this is one rotation and then 2 rotations. There's ways where you can just put those rotations into the object because it's just abstract. Like you can represent any, if it's logically consistent, you can represent some action as a number. And we're going to evaluate polynomials at not at numbers, but something that's not too dissimilar. In the next session, not today. And we come to the Schwartz-Zippel lemma. Firstly, the name might be a little scary, but it's just the names of the discoverers. I mean, I guess they were German, Schwartz and Zippel. I think on the Wikipedia page there's also a third name, but they're just the names of the discoverers. So don't worry too much about that. But yeah, it gets kind of more complex. It's never particularly easy. But this idea is like very core to how PLONK and also a lot of other proof systems work. It's not the only piece, but it is one of the key pieces. The core idea of this theory, also just quickly for the naming, this is called a lemma. So I mean, you probably know what theorem means. It's like some idea that we sort of think is, have proven to be true. In maths, we also have a lemma, which is actually the same thing as a theorem, but usually we reserve theorem for like a more important idea, and the lemma is just a less important idea to help prove a theorem. But this lemma is actually particularly important. So you can just think of, instead of the word lemma, just think of the word theorem. So what it says is that if you have 2 different polynomials, but those polynomials have the same degree, remember which is the highest power, and you evaluate them at a random point, and the evaluations at that random point are the same, then with overwhelming likelihood, the polynomials are the same. And if you remember from last session, we said that what a proof says is that with 99.99999, etc., percentage likelihood, the computation was done correctly, or the proof is valid, or the person knows the thing. That probabilistic part is coming from this lemma. When it says with overwhelming likelihood, we actually know the exact probability of it passing by accident, and we can make that probability arbitrarily small. Okay, so this is like one of the core ideas in the proof aspect. Yeah, we're going to sketch out what the core idea is, so it's a bit clearer. The way I phrased the lemma is only true if the field is large enough. Because if you've got a small field, like in the one we're working with 11 elements, there's a good chance that just by chance you're going to end up at one of those 11, one of the 11 elements that was correct. But we usually work with huge fields that have like 10 to the 80 elements, and so there it's going to be like insanely small, and we can work out the exact probability. Okay, let's explore what that means. We'll start. Let's Schwartz-Zippel lemma. So the sort of statement of the core idea, if we have f of x in R, okay, let me not introduce more notation. F of x and g of x both in Fp with x, these polynomial rings, and P is just some arbitrary prime number, and the degree of F is the same as the degree of G. Okay, and then we get take a random R in Fp, so a random number in Fp. Now here's the statement. If f of R equals g of R, then the polynomials are the same. F of x equals g of x. And we can say this in different ways, like the more specific part, we could say with overwhelming likelihood. But we don't have to say with overwhelming likelihood. We can actually work out like the exact probability of that happening. The exact probability would be the degree the degree of f, because it's the same as g, over p. Okay. In practice, so remember p is the size of the field. In practice, these values might be around the degree of f might be around 2 to the 30. F is going to have like the highest power of x will be in the in millions. And p, well, we just said before, it's going to be like 10 to the 70-ish, but you can also think of it 2 to the 256 maybe. So, and that equals around what, 1 over 2 to the 226. Like a really, really large number. This is going to be the likelihood, like a more specific likelihood of this happening by accident, and that is just phenomenally unlikely. Not going to happen. Okay. So we're going to explore a little bit as to why that's true and try and present a visual proof, because I told you that this is the probability, but why is that the probability, and how can we have some intuition for that? If we look at functions or polynomials, I mean, just going back to the slides, we have two images. In the left image, we have f of x equals x, and then we have f of x equals x squared. We're going to be looking at like the bendiness, or how many bends these have. So f of x equals x. If we sketch it out, apologies for the quality of sketches, but this is going to be a straight line like that. I mean, maybe let's just do the lines themselves as different colors. Okay, straight line, no bends. F of x equals x squared. If we sketch that out, you'll get something like this. And you're going to see, you see that we have 1 bend, 0 bends. Go a bit further, do f. I'm not going to write out the exact, I don't know the exact equation, but we're going to have x cubed plus, I'm just going to say ax squared plus bx plus c. And a and b and c are arbitrary terms. I don't know their exact values. I'm going to explain why I'm doing that right now. Basically, I want this curve is going to look like this. Okay, you see here that we have two bends. The reason I didn't just do g of x equals x cubed is because if I sketch that, it just looks like this. And it doesn't really have any bends. And it breaks the rule I'm trying to show you a little bit. But what the pattern you'll see emerging is that the polynomial can have up to a certain number of bends. So if something has degree 3, like this here, degree 3 because the highest power is 3, it can have at most 2 bends. It doesn't necessarily have 2 bends, but it can have at most 2 bends, which is why this example didn't work perfectly. Right, so we see that the rule is a degree d polynomial can have at most d minus 1 bends. Okay. So the polynomials, when we draw their graphs out, they're going to have a certain number of bends. Okay, let's explore what actually happens in the exact space. Now, if I draw out, so now I'm drawing out not negative on either side, because remember we're actually working in FP, which is a field, so we don't actually treat it as having negative numbers. It just goes from 0 all the way up to p minus 1. And the same on this side, p minus 1, this is still FP. We can even sketch out like a little dotted line for the limit of it. Okay, so we don't actually need to work in the negative part. So if we have 2 polynomials, let's do f of x, and we also have g of x, and let's say that d equals 3 in this scenario. If we're to draw the graphs of these 2 functions, right now we don't know what they actually look like, but we do know one thing now. It's going to have at most 2 bends. So if we do f of x, okay, we've got our 2 bends. Here's 1, and here's 2. And then we can draw up g. Again, it can look like anything, but okay, it can have at most 2 bends. It's bend 1. Oh, not very visible, but bend 2. So remember that what the theorem is saying, if we take random r in here, all right, we're going to take a random r, which is the same as just taking a random point here. If we just go back and forth and then stop somewhere, and let's say we stop here, do that a different color. We just stop here. Then if we go up, we're expecting, and we see these 2 to be the same, that's going to be when the theorem applies, because remember it has this if-then. If the evaluation is the same, then the value is the same. But if these 2 polynomials, if they're degree 3, they have at most 2 bends. Because of that, they can only overlap in at most 3 places. 1, 2, 3 here. Okay. These can only overlap in at most 3 places. The only way two polynomials that have the same degree can overlap in more places than their degree is if they're the same polynomial. Of course, if g of x equals f of x, then the drawing of g of x would be just going over f of x. Okay, then they're the same everywhere. Okay, but if they're not the same, they can only overlap each other in 3 places now. Okay, and that's why if we're going to take a random value somewhere on the bottom and then look at it and then go upwards, the likelihood that we chose this random value to be one of the 3 locations where they actually overlap is just phenomenally unlikely. Again, we can work out exactly, like here we have 3. There's 3 possible positions where they overlap. So the top is 3. And the total space is P, which again, we're going to do 3 over 2 to the 256. You know, it's like you take a random atom from this universe and expect it to be the one you were hoping it to be. You know, that's the scale of this. So this, again, is where the probabilistic aspect of proofs come from. We know that guessing the correct answer, in fact, you're not even guessing the correct answer because the number is taken at random. Like if this wasn't random and I could just choose it, I could just choose one of these overlapping coordinates. You know, I would just choose the value that would make it pass. But we don't get to choose. It's going to be random, and it's forced to be random by a technique we call the Fiat-Shamir transform, where we're just going to like hash stuff to get a random value. Okay. So because I can't choose I can't choose the value myself, and it's taken at random, the likelihood that this random value is one of the tiny situations where these polynomials evaluate to the same. We get out the probabilistic aspect we want. So hopefully this kind of visual sketch helps you understand why that is the case. In general, when we actually prove this, I didn't want to do that because it makes it a bit more... the proof is actually cleaner, but you have to do a few more steps. If you're just to look at the difference between these 2 polynomials, for people interested in the mathematics, if you look at the difference between these 2 polynomials, you'll get a polynomial that will be at most degree 3 as well. And then that can only cross the B0 in at most 3 places, is the simplest way to prove this. But this is like a more visual... You can see that these drawings can't overlap in more than 3 places. Okay, so that's what we're going to be using later to make the claim that because these values are the same, the polynomials must be the same, and therefore the computation was done correctly. Of course, there's a lot more steps even in between making the computation, the circuit arithmetization, and getting to those specific polynomials. Okay, but you see, we just keep growing and building on these ideas. We had the modular arithmetic scenario, and then we built groups on top of that, and then we put groups together to get fields, and then the fields are the sort of the number system we use in our polynomials, and now we have a theory about polynomials, and then we're going to do lots of other stuff with polynomials. A lot of what happens in SNARKs can be thought of as creating and playing around with polynomials. So yeah, the more comfortable you are with these ideas, the better. And that's kind of everything I wanted to go over today. I think it might be best if I just tell you the homework quickly. I mean, maybe you can snap a photo. The same as before. These ideas are not straightforward. the more time you spend with them, the better. And the more examples you can remember, the better. That's actually what happens a lot of the time, that you're trying to think like, is this a group or is this a field? You'll be like, well, I remember in this example, F5 or a group with 3 elements. It makes processing it a lot easier in the beginning if you just commit a few examples to memory, particularly also the definition. Like if you want to check if something's a group or a field, you've got to remember what that actually entails. On top of trying to remember things, it would be really good to play around with another one. I mean, I did the set with 6 elements here in the question, but you can do it with any one you want. And then if you turn those into Anki cards, it'll be really, really good. So we didn't actually share the slides last time. So, I mean, we can share the slides, but if you want the homework, it might be quicker for you just to take a screenshot. So thank you for coming to this session. Just before I answer questions, I want to recap. So in the first session, we did like more high-level idea. What is a proof really doing, and what are some of the consequences of that? And in this session, we're starting to get going with some of the fundamental mathematical ideas or objects that we use. And then in the next session, we're going to build up more complex ideas about how we work with these mathematical objects to do some of the things that we do with the inner workings of SNARKs. And in the last session, we'll have a quick look at how those are all put together in PLONK itself. And then we're going to do a brief overview of a few different proof systems out there in the space. But again, I mean, I keep emphasizing this, but no one ever like looks at the definition of a group and a field and be like, oh yeah, cool. And then they can just work with it. It takes, a bit of effort to be more comfortable with these ideas. So now we can just kind of go on to questions, and I'll stick around for, as long as people want to keep answering questions. So no one's asking if we can think of a field as 2-dimensional. I think I would actually personally say no. Usually when I think of a dimension, I think of like a way of representing the elements in 2 dimensions. But if I'm thinking of 2 dimensions, I'm thinking of like representing stuff in 2 different like axes, sort of thing. But I think there's more like 2 perspectives on what you can do with the things in a field, because you can use one binary operation or the other. If thinking about it as 2-dimensional, if you find a way that's kind of logically consistent, then go for it. And also in this time now, if you want me to go over anything we went over, or if you want me to do another example of one of the things, we can try that. Yeah, that's good to hear. The visualization was helpful. Yeah, there's a lot of the probabilistic aspect coming from there. But it's also the same kind of idea. The fact that you have this huge space makes it hard to figure out like what the input was. That's where the secrets come from as well. Like it's all kind of very connected to each other. Yeah, but we'll see in a bit more detail next session as well when we bring in elliptic curves, and then kind of start to understand a bit more of what's going on. So the elliptic curve, there's going to be a group there, and we're going to have something called elliptic curve addition, but it's not going to be normal addition as we're used to it. It will be like a different type of binary operation. Yeah, anything from 3 blue 1 brown is like solid quality content, like really good maths YouTuber. In fact, the visuals I made in the online content, he like built the software. I think he worked at Khan Academy for a bit, where it's like kind of sketching on tablets like I was doing here, and then he thought there was a better way to do it because he's like a maths computer science major. So then he kind of built his own software. So you write these animations in Python, and they're very high quality. It's called Manim, mathematical animation. So it's a Python library, and then you can build these really, really nice visualizations. Everything I made in the course content is from there. But he like made the software, so he's like phenomenal at it, and he's like made incredible visualizations. Not just that he's made incredible visualizations, but also that he explains it in an amazing way with like really fitting visualizations. I think the video there is also talking about these rotations as a group. So yeah, any content from him is like very much worthwhile to take a look at. But yeah, having visual ideas, visual representations of some group elements and some examples is like very helpful for your group understanding. But don't forget to also play around with a group yourself and like just check if a few things are a group. Is going to be sort of essential. And Zeke, friendly, your question, if the degrees have to be equal, they do have to be equal, because if they're not equal, then they're definitely not the same polynomial. If one is highest power is x to the 30 and the other is x to the 29, then by definition, we know there's a term that doesn't match between them. Yeah. Yeah. So, you can sort of drop that requirement anyway. Like, if you just say they have a maximum degree of like 1,000,000, if they have a maximum degree of 1,000,000, then the same if-then statement is still going to apply, because this math here will change. Instead of 3 over 2 to the 256, you'll have 1,000,000 over 2 to the 256. And 1,000,000's a lot bigger than 3, but 2 to the 256 is still a massive number, and this will still be like 0.0000, and just go on for ages. So that will actually still be safe, as long as the degree above is bounded. Right, because the polynomials can overlap. F and G can overlap. Because they're degree 3, they can overlap in most three places. The degree kind of specifies how many places they can overlap. And if you don't have a maximum bound, these can be different polynomials, but if their degree equals 2 to the 256 minus 1, which is just like an insanely large polynomial that we can never evaluate it because it's too big, unless it's very sparse, where most of the terms are 0, then these two polynomials will actually overlap everywhere on the curve in our space except for one point. So the degree, we don't necessarily need them to be equal, but it has to be bounded. Thank you, Alex. Like I said, you can always ask questions in the intro to SNARKs chat. If you @ me in there, I'll get a notification and I should respond pretty quickly. And yeah, please try and get used to some of these ideas. We're just going to keep building on them. And elliptic curves are not straightforward either. But next session should be the next hard session. It'll be the same time, 8 p.m. on Thursday. Next session is going to be tough again in terms of mathematical content, but then the fourth session, not that it'll be easy, but it won't be like as intense. I know when all these ideas are introduced in the beginning, you're just a bit like, what is going on? But the more examples you see, the more you'll get used to it. And even if you don't understand it perfectly now, if you try and put in some work and then later on you'll do another course, when you start that course, you'll be like in much better position to take on everything and just keep expanding your knowledge base. Perfect. Well, question sort of slowed down. I'll probably hop off now, but again, you can just ping my name in the chat and I will respond quickly. So thank you all again for coming. And yeah, we will see you on Thursday.